All right, so yesterday we left off talking about how to add and subtract significant figures and multiply and divide them. So with multiplying and dividing, our answer can only be as accurate as what? The least accurate number or the least precise number. And how do we know which one is the least precise? The one with the... Not for multiplying and dividing. The least number of significant figures. Okay? So when we multiply and divide numbers or measurements, we go by our answer can only have as many significant figures as the least number of significant figures in the problem. Okay, so what about adding and subtracting? Our answer can only have what?
Least amount of digits.
Least amount of decimal places. That's correct. So our answer has to have the smallest number of decimal places, the same number as the smallest number of decimal places. So if we were to add up, well, if we use their numbers again, we were to add up 16.74, 5.1, and 21.8. How many decimal places should my answer have? 1. Because 1 is the least number of decimal places in 2 of my measurements. So my answer should only have 1 decimal place. Good. All right, so scientific notation should be a lot of review for y'all. So I'm going to go through it pretty quick. But, with scientific notation, that you just take, it's usually you have a number between 1 and 10. And then out beside that, you have the power of 10. And the power of 10 tells you how many places you moved the decimal to get behind that first non-zero digit. So if we use the example of 2,500, okay, and the decimal is behind or at the end of that number, then we're going to move that decimal 1, 2, 3 places. It needs to be behind the first the first digit. It needs to be behind the first digit in the number. Okay, so that's what we mean by it has to be between 1 and 10. It can't be behind the 5. It can't be 25. It has to be between the 2 and the 5. So it has to be a digit between 1 and 10, and then your decimal place. So we had to move it 3 places to the left. So that means it's going to be 2.5 times 10 to the 3, because we went 3 places to the left. If it's to the 3, then that means it's positive. Oh, I got a sick grandbaby. She has her first cold and fever. So she just sent me pictures. Her eyes were all swollen and red, and I know, it's pitiful. She didn't take her to the doctor. But she's on the mend, I think. All right, so here is our answer, 2.5 times 10 to the 3. Now, the other good thing about writing numbers in scientific notation is the number part, all of those digits in there are significant. We have to write them as significant. So when we say 2.5 times 10 to the 3, how many significant digits are in that number? 2. The 2 and the 5. All right, so what if I wrote this? What if I wrote, let me erase that. What if I wrote 2.50 times 10 to the 3? How many numbers are significant? 3. Because the 0 is behind the number and behind the decimal, then it makes it significant. So those are 3 significant figures. I'm sure in my measurement that the 2 is right, the 5 is right, and the 0 is the one I'm uncertain about. So all of those are significant. Yes, ma'am.
So what if it's like 0.005? Like
Okay,
how
so-
many of those are?
Okay. That one isn't going to be scientific notation, but if you're just talking about looking at the number, 0.005, is that what you're saying?
Yes, ma'am. Or just
Okay.
any zeros after the decimal but before the numbers.
Okay. Any zeros after decimal, but before the number. I just had brain. Hang on.
Those are significant.
Let me think on that. Yeah, those are significant. Yes. It's the ones after that that may not be.
Okay. Would the 2.50 not be like an incorrect scientific notation though? Like
No, it'd be fine.
Oh, you can leave an O there?
Mhm.
Or zero, sorry.
Yes. Now, see, this is where kids get confused with math. Because what have you always been taught in math? You can drop it off. Doesn't matter, right? But if it's a measurement, it matters because I know I'm measuring out to the hundredths place. And you have to indicate that you're measuring out to the hundredths place with certainty. Okay, so you can't just drop it off. So what if we had 2.500 times 10 to the third? How many significant figures would that be? 4. And the reason that it's 4 is because I'm saying in that measurement, I am sure that I measured out to the thousandths place with precision. So I'm sure about that last decimal place, and that's why I have to write it down. Okay. All right. So let's clear that screen. Go back. All right, order of magnitude. Remember, order of magnitude is just a power of 10. And so sometimes we can use order of magnitude to get an estimation of something or get in the ballpark where you may be off by some, but it's okay. Okay. So there's an example. We're not going to have to do that a whole lot, but there's an example of what we're talking about with that. Suppose you want to estimate the speed of a cliff diver on entering the water. First, the cliff may be 10 meters high. It's not going to be 1 meter because 1 meter is not a cliff, right? That's just a step. It's probably not going to be higher than 10 to the 2 meters because that's 100 meters. That's really tall. Okay? So most of the time, somebody's not going to dive off a cliff that's on 100 meters high. So we don't need to worry about that number. And that 1 is too small, so that's why we estimate probably around 10. Okay? Then the diver hits the water in something like 1 second. So again, we're going to estimate 1 second. It's probably not going to be 0.1 seconds because that's too short of a time. And it's probably not going to be 10 seconds because that would be a long time in the air. Okay? So we estimate 1 second. So we're estimating his speed when he hits the water is going to be the 10 meters for how tall the cliff is, and the 1 second for the time he spent in the air. And that's just an estimate. We could be off. But we're using powers of 10 to make that math really easy. Okay? All right. Okay, we'll move on from that. Graphing. The reason we graph things is to see trends easily. So we have a data table, and when we can see a trend, but if we put it in a graph, we can see that trend really easily, and we can also get a lot more information about it. Slope is really, really important. So knowing how to find the slope of something is going to be very important because in here, the slope is not just the word slope. It's actually going to mean something. It's going to show a relationship between two things. Okay, so if you look at this graph, we are graphing velocity and time, okay, or speed and time. So the slope of that line is going to mean something. It's going to be a constant number. Okay? All right. Whoops, wait a minute. So by looking at this, you can predict how fast is the ball going to go in 7 seconds. How did you get that?
Each time it's like passes 1 second, it's 10 meters per second.
Exactly. You can see the trend, and you can see that even though 7 is not on this graph, we can still predict what it should be by looking at what happens every other time. Okay? So it's going up 10 meters per second each time, so by the time we get to 7, it should be 70 meters per second. That's called extrapolation. So we're looking at something beyond what's actually on the graph. It's extra, beyond the graph. But we're assuming the trend's going to be the same, so we just follow that. What about at 2.5 seconds? $25. How'd you get that? It's on the graph. Well, how did you find it? On the graph. Be very specific. Huh? I went over to 2.5, and then what did I do? Go up. And then what? Go up. And that should hit right at about 25. Okay? That's called interpolation, because I'm doing something within the graph. I'm looking at a number that's within the graph. Okay? All right. So in general, linear relationships are going to exist between two quantities that form a straight line. So y'all know that. You might, if you got to write that down, that's fine. But just remember, linear means it's a straight line, and it shows a relationship between those two things. And that relationship is a straight line. Okay? Unfortunately, not all graphs are straight lines. Sometimes they are curved lines. Okay? So let's look at this example. All right, so suppose we measure the distance covered by a soccer ball, and we plot the data during each second of the ball's motion. We call this a nonlinear graph, obvious reasons. It's also called a parabolic relationship. So if you remember back to algebra, what's a parabola? Where it makes that little U shape. And what we have is half of a parabola right here. Okay, so it's a parabolic relationship. Okay. So if a graph is not constant or is not linear, then the upward shape is a parabola, and this is the general formula. You're going to have an exponent in there. So if you go back and think about your algebra, slope-intercept, y equals mx plus b, that's only for what? Straight lines. Those are linear graphs. But you have general equations for parabolas and hyperbolas and all of those other things too. If you got a parabola, you are going to have an exponent in there, right? So we say that it's the position on that graph is equal to some constant times t squared. The square is what makes it go up in that parabola shape rather than being a straight line, okay? So anytime you see that, you ought to associate that, oh, okay, this is a parabola, we got a square, we got an exponent in here somewhere. It's not just y equals mx plus b, okay? So I would draw me a little sketch of the parabola graph, and then I would put this little formula out beside it, and if I'm taking notes, and so that you make sure you understand that relationship. Parabola means you're going to have a square in there. You're going to have an exponent in there. This is just math related. Does anybody know what this constant is going to do to my parabola?
Change the y value.
It's going to change the y value. So what does that do to the shape of the parabola? It's going to make it wider, or it's going to make it narrower. What if we had a negative in front of that? What would that do to flip? It would flip it upside down. Right. Okay. Good. Oops. Okay, so this would be, finally, we can do measurements of volume of a container with pressure. So that should look kind of familiar from chemistry because remember, pressure and volume are indirectly related. Okay, so as volume increases, pressure goes down. And that's what you see on the graph. Okay, so as we go up in volume, our pressure goes down. So that's an inverse relationship. Okay. And then so here is our equation. The pressure is equal to some constant divided by the volume. So if it's an inverse relationship, you're going to get that hyperbola. Remember those are from, that's not geometry, that's algebra 2. But that's a hyperbola. So as one thing goes up, the other thing goes down, and you make that hyperbola type shape. Okay.
So,
Yes.
do they write constant just to avoid having a ton of x's?
They write constant because that's going to be a set number all the time. So when we did ideal gas law, remember, was PV equals nRT, and that was a constant. It was the same number all the time, right? So that's what they're talking about, that there's going to be some number that's the same all the time that you're going to put in there. A lot of the constants that you'll use in here, speed of light is a constant. It doesn't change. Acceleration due to gravity does not change. That'll be another constant that you memorize and that you'll be putting in. So that when they're writing a constant, that's what they're talking about, a value that doesn't change. Okay. All right, so this is going to be new. You probably not used or heard these words before. So scalar quantities are quantities that are represented by a number with a unit. So if I measure something and I say it is 48 meters, that is what we call a scalar quantity. It's a number and a unit, and that's it. Okay? So if I'm measuring the distance of this room from here to this wall, that is a scalar quantity. I would just take my ruler and I would measure that distance. Okay? And here's some other examples of scalar quantities. Temperature, speed. If I'm driving down the road and my speedometer says I'm going 25 meters per second, that's a scalar, or I think that's what we did yesterday, 65 miles per hour, what we're used to saying. That's a scalar quantity. It's a number and a unit, and that's all it tells me, okay? So other quantities, though, are known as vectors. So vectors are things that have a numerical value with its unit and a direction. Okay, so it's a way to get things a little more specific. So I can say I'm going 65 miles an hour down the highway. What does that tell you? It tells me how fast I go. Does it tell me where I'm going? Does it tell me anything else at all? I'm on the highway. But there's lots of highways, right? Highways go in all 4 directions. So if I want, that's a scalar quantity. But if I'm saying I'm going north on I-65 at 65 miles per hour, what does that tell me? You know which direction on 65 I'm going. I'm traveling north. Okay? So that is a vector quantity because it tells me the direction in which I'm going. Okay? Now, When I say north, that's kind of a vague direction, just north. When we do problems with these, not only are we going to have north or south or east or west, we're going to have a degrees associated with it. You know, you might be going 50 degrees north, 40 degrees, whatever, okay? So we're going to get kind of specific with that later on. So here's our example. Speed of a car is 25 meters per second, but if we combine that with a direction, we have to write out both. So for it to be a vector quantity, you have to write the number, the unit, and the direction. Okay, so 25 meters per second, north. You can put a capital N or S or whatever, but you have to put the direction for a vector. Velocity, okay, so you might want to make a note of this because a lot of times people will get this confused. Velocity is a vector quantity. Speed is a scalar quantity. Velocity tells me how fast I'm going and in what direction. Okay? But speed just tells me how fast I'm going. Yes?
So, question. So velocity, okay, so that stems from the word vector, I guess.
Well, yeah.
So,
But there's other vector quantities.
is velocity just like the dimension of like speed or whatever, while vectors could be whatever other dimension, whatever?
Exactly, yes.
Okay.
Yes, we can have other types of dimensions that are, and we're going to have other types of dimensions that are vector quantities. We talk about different forces. We talk about force of friction, and those are the two that pop in my head right now.
But velocity is specifically like.
Velocity is how fast you're going and in what direction. Yes. Okay, so everybody have this down? Because this is kind of new stuff that we need to make sure we have written down. Everybody got it? Okay. The key to remember is that vectors, and we've already talked about this, vectors have a numerical value, and we call that a magnitude. So you might want to jot that down just because that's a term that you might hear. The numerical value on something is called its magnitude and direction. So vectors have magnitude and direction. Scalars just have magnitude. Magnitude means the number and its units. That's it. So if I'm going 65 miles per hour north, what's the magnitude of that?
65
The 65 miles per hour. Okay? The direction is the north part. So vectors have magnitude and direction. Scalar just have magnitude. I think that's going to take us through 1.4. 1.5 is really short because it's just listing out some problem solving skills, and then we're going to actually start working some problems because the best way to learn problem solving skills is to work problems, unfortunately. So does everybody have this down? So the only thing in 1.5 we're going to do is I'm going to give you a list of skills, problem-solving skills or steps to take, and then we'll just spend the rest of the time looking at problems. All right.